Hey, VStat. Before we begin today's lesson on chi-squares, got a good question for you. Chi-squares is a whole new distribution, but I want you to know when to use a z distribution, a t distribution, and a chi-square distribution. Let's go backwards a bit. A z distribution is based on z-score, and z-score is based on a normal curve. A z-distribution is basically your default distribution. It's pretty much the one you're going to use most of the time. So that's pretty much your go-to distribution. Since this class is based on a normal curve, you would use a z-distribution, z-star values, that's at 1.96 and so forth, and z-scores all the time. T-distribution is a bit more specific. You're usually going to use t-distribution in one of two situations. First situation is this situation. In this z-statistic, which is basically the same thing as z-score, but it's talking about a statistic in a whole sample group, notice how we know the population standard deviation, or we know lowercase sigma. The only time you're going to use, well, one of the only times you're going to use t-statistics or t-distributions is if you don't know the population standard deviation. So you have to take a sample within that population and use that sample standard deviation. And that sample standard deviation is going to be good enough, especially if you get a really large data set, like an n being 10 or 15 or 20 or 30 or 40 or 50. You got a big value of n, it can get you closer and closer to the z distribution anyway. So we like this. Remember, this is found when a guy was trying to make beer, and he was trying to figure out how to make a better beer. And he didn't have the whole population of the beer. He could only take samples. And using that sample, he had a good idea of what the whole beer company was doing when it was working for him. And that's the root of this distribution, and that's why we use it. We don't know the population standard deviation, but we only have a sample standard deviation. That's the one case, one scenario you use t distributions. The other scenario is this one. All right, in this case, we're looking for the difference between two fields. In this case, we're looking for the difference between two means. If you're looking for the difference between two means, as in mean in field A and the mean in field B, this is always going to be a t-distribution. You're going to use a t-distribution formula, you're going to calculate that t distribution value and so forth to use the t-distribution table. So we're looking for the difference of two means, and they got to give it to you somehow, somewhere. Either got to tell you the means, or I have to give you a way of calculating the means to find a difference to those two means. Then you use t-distributions. They may give it to you this way, or they may show it to you this way. See how this is giving you two box plots? These don't include mean, they include medians. So at some point they have to tell you the mean. And on the page, someplace on the test, they'll eventually give you the mean. And here's the mean of non-athletes, mean of athletes, and you have all the information about the mean. Then, once you see you comparing those two groups, and you're comparing their means and find the difference of those means, you know that is a t-distribution situation. Now, the one you'll learn today is when to use the chi-square distribution. Chi-square distribution is going to be used when you're not necessarily comparing the means, but you are comparing different categories, different situations over different categories. Here you got area 1, area 2, area 3. These are different categories, right? You may be comparing Monday, Tuesday, Wednesday, Thursday, Friday. Those are different categorical data sets. You may be comparing the difference between SAT score, ACT score, and graduate record exam score, and MCAT score, and LSAT score. All those are different categories, and we can compare those using chi-squares. So for using chi-squares, just know you're looking for a situation where you're comparing things over multiple categories. Maybe it's birth months, maybe it is gender, and so forth, but different categories. All right, now take a look at this example. This looks like it's going to be a t-distribution, a z-distribution, or a chi-square distribution, just by looking at how the picture is set up. All right, you probably said it's got to be chi-square because it's not comparing difference of means, and it's not comparing anything with mean and standard deviations. It's definitely comparing categories, Monday, Tuesday, Wednesday, Thursday, Friday. That is a chi-square distribution situation. And the good thing is, this is our first example for today. All right, so let's get started. Hey students, we're going to go one step further with chi-squareds, and we're going to apply that to hypothesis testing. So here's our first example for the chi-square test. A school principal would like to know which days of the week students would likely be absent. The principal expects that students will be absent equally during the 5 days of the week. The principal selected a random sample of 90 teachers, asking them which day of the week had the highest number of absences. The observed and expected result is shown on the table below. Based on these results, do the days for the highest number of absences occur with equal frequencies using a 1% significance level? All right, so this is what we have. So we observed they had 22 days, 14 days, 12, 16, and 26. We expected 18 each day. And this is how they came up with the expected number. The expected number comes from finding the sum of all the numbers in this list, then divided by the total number of categories. So if I looked at the sum of all the numbers in that list, it's 90. Since we have 5 days of the week we go to school, it's 90 divided by 5, which is 18 days. So our expected number of absences equally distributed is 18 days. So we learned in last class how to find the sum of all the observed values, take away the expected values, divided by the expected values, and it's going to be squared. We want to find the sum of all those. So basically, that's going to be the observed is 22, take away 18, that's 4 squared, and we expect it to be 18. The next observed is 14 take away 18, so that's negative 4 to the second over 18. The next one is 12 take away 18, that's negative 6 to the second over 18. And the next one is 16 take away 12, which is negative 2 to the second over 18. And the last day is 26 take away 18, which is 8 to the second over 18. And we'll plug this in our calculator, and we'll find the sum there. This is going to be our chi-squared value. So chi-squared is equal to that sum. When I plug it in, assuming it's all done correctly, our chi-squared will be 7.55. Now, what we need now is chi-squared is not a normal curve. It's skewed. And we have to consider our degrees of freedom. Our degrees of freedom is still n minus 1. But n in this case is the number of categories. The categories here we have is 5. So it's 5 minus 1. So the degree of freedom is 4. From there, know our degrees of freedom. And they told us our significance level. They said our significance level was 1%, which is 0.01. We can use that to find our critical value on the chi-square table. Now this number on the chi-square table is our critical value on right CV. We're going to find that number by using our degrees of freedom and our alpha level, our significance level. All right, so here's our degrees of freedom. In this case, it was 4. And our significance level is here. So we're looking for our significance level of 1%. And 0.01 is right there. So if I look at that line, that's 13.277. That is our critical value. 13.277. This area of our critical value, if we get a value that falls here, we reject the null. This is our reject section. Anything above that critical value, we reject the null. This part is our not, or do not reject section. Anything that falls below 13.277, we do not reject the null, or we fail to reject the null. In this case, our chi-square value was 7.55. It's probably around here. That value falls in our do not reject the null. So now that we established that, let's go backwards. Let's decide our null. In the original problem, it says that a school principal would like to know which days of the week students will likely be absent. The principal expects students will be equally absent all 5 days of the week. So our null is students are equally absent all 5 days of the week. All 5 days. Our alternative is students are not equally absent all 5 days. Given the fact that our chi-square value is in our do not reject region, we could conclude that there's statistical evidence that suggests that students are equally absent all 5 days of the week. So I just wrote the conclusion. There's statistical evidence that suggests that students are equally absent all 5 days of the week. That's all I have on that. Let's move on. That's a great example, and we can do this with our calculator as well. This is how it looks if we did it with our calculator. Turn the calculator on and make a list for the observed and expected. Go to Stat, Edit, and the observed is 22, 14, 12, 16, 26. Our expected, we write the same number each time. It was 18. So we go straight down the list, type in 18. Until I get to the bottom list, and then match up equally. From there, let's leave the screen. So second mode to quit. It's always good when you're doing these statistical tests to clear out your calculator so nothing's being already there and messing with your data. So from there, we'll go to Stat, we'll go over to Test. We want to go down until we see the chi-squared goodness of fit test. So there it is, that letter D. We'll hit enter. I want my observed value to be list 1, so it's second number 1. I want my expected value to be list 2, so it's second number 2. My degrees of freedom in this case was 4. And then I can calculate. And we notice it tells us automatically our chi-squared value. And it also tells us the probability of that happening. Since that probability is bigger than 0.5, but its significance level is 1%, so since it's bigger than 0.01, this is not unusual. Hence, we fail to reject the null. Let's look at a new example. This example comes straight from the textbook, and it's a famous question that was actually posed in the book called Outliers by Malcolm Gladwell. If you haven't read it, you should check it out, or at least get the audiobook. It's very interesting. In his book, Outliers, Malcolm Gladwell suggests that hockey players' birth month has a big influence on his chance of making it to the highest level of the game. Specifically, because January 1st is the cutoff date for youth leagues in Canada, where many National Hockey League players are from. Players born in January would be competing against players up to 12 months younger than them. The older players tend to be bigger, stronger, and more coordinated, and hence get more playing time, more coaching, and have a better chance of being successful. The C of birth date is related to success judged by whether a player makes it to the NHL. A random sample of 80 National League players from a recent season were selected and their birthdays were recorded. The one-way table below summarizes the data of the birthdays for these 80 players. So here they are. This chart shows that 32 players were born between January to March, and 12 players were born between October and December. Just looking at it, you may think January and March is clearly a lot bigger group of people than there are in July to September, which would be late summer, and October to December, which would be early fall. But let's use statistics to prove it. So it says, do these data provide convincing evidence that the birthdays of National League players are not uniformly distributed throughout the year. Let's treat this as a free response question on the AP exam. So we're going to start with our state, plan, do, and conclude. Let's start with state, the hypothesis, and the null hypothesis. Hypothesis is going to be that all players are equally likely to make it to the National Hockey League, no matter their birth month. I'm going to say something along those lines for my null hypothesis. So my null hypothesis is all players are equally likely to make it to the NHL, no matter what time of the year that they were born. The alternative would say pretty much the opposite of that. Birthday does have an effect on making it to the NHL. Next thing I'm going to do is plan. My plan is to conduct a chi-square goodness of fit test. Then let's go to do. So do, I'm going to find chi-squared, and I could do the summation thing. Summation of all the observed, take away expected, divided by the expected. Could do that to find my chi-squared. But since we have a calculator, why would I? So I'm going to do a plan of use the chi-square goodness of fit test. So I need to make two lists. And the lists are going to be the data from the table. Let's start there. So I'm going to clear out what I have currently. So clear, not delete. And it says 32, 20, 16, and 12. Since they're equally likely, this should be equally spread out. So my expected value should be the average of all of those. Some lists you might be very long, so we can find that summation or average very quickly. So if I hit stat, then calculate, stat, and then calculate one variable statistics with list 1, it tells me that my mean is 20. So my expected value is 20. So I'm going to go to my list 1, list 2. I'm just placing in 20 for all those. So after I do that, I can quit. I go to stat, test, and go down to chi-squared, goodness of fit test. List 1, list 2. In this case, our degrees of freedom is 1, 2, 3, 4. So our degrees of freedom would be 3. And we're looking at that, chi-squared is 11.2. So our chi-squared value is 11.2. And the probability of that happening is it's smaller than 5%. It's slightly bigger than 1%, but we typically use a 95% confidence interval. I got enough information to say we're going to reject the null. So we should write down my probability though was 0.01, or basically 0.01. This is chi-squared. I'm going to put it on a graph too though. In this case, AP readers want to see the graph. I'm going to put my critical value. I'm going to put the value that I found. So going back to my chi-square table, again, our degrees of freedom was 3, and chi-squared, and our significance level we're using could be 95% confidence, or alpha level being 5%. So let's stick with alpha level being 5%. That should be good enough. So 0.05. So here's degrees of freedom being 3. And here is 0.05 right here. So the alpha level we're concerned with, well, that's critical value, 7.815. This is 7.815. So this is my critical value. So anything bigger than 7.815, we're going to throw away. We're going to reject. And 11.2 will definitely be right here. So it's definitely in the reject category. So no doubt we got to reject it. So we got it multiple ways. We can prove it by probability being less than 0.5, 0.05, and we can prove it by showing that this falls above the critical value, given that significance level and given that degrees of freedom. So in this case, we will reject the null. You have to put it back into words for my conclusion. So here's my conclusion. It's our final step, which is conclude. So my conclusion is there's statistical evidence that proves is too strong a word because it's statistics, and we're all about having a good guess. So that suggests that what time of the year you were born does impact your chances of making to the NHL. So that's our conclusion for that statement. Also, 80 times 10 has to be less than or equal to 10% of the whole population to make sure everything, because we're doing sampling and replacement, we have to make sure we don't have more than 10% of the population, or at most 10%. If you Google how many players in the National Hockey League, I think it's about 876 players. 80 times 10 is 800, and that is less than 10% of all the players in the National Hockey League. You can make sure it's random, and they also mentioned that they were randomly selected someplace in the problem, a random sample. You don't have to check for normality because chi-squared is not a normal curve. So I would make sure I mention these things, and I'll explain why I did this too. I wouldn't just say 800, whatever. I'll explain what this is doing if this was a free response question on the test. With that said, you know enough to try this final example. So here's the example that deals with astrology signs. So you're going to do this on your own, but the question says, what's your sign? The University of Chicago General Survey, GSS, is the nation's most important social science sample survey. For reasons known only to social scientists, the GSS regularly asks a random sample of people their astrology sign. So I got all the Aquarius and Gemini and so forth. If the births are spread out uniformly across the year, we expect all 12 signs to be equally likely. Do these data provide convincing evidence that all 12 signs are not equally likely? And then it says, if you find significance, perform the follow-up analysis. So basically they're saying, do all the things we just did with plan, state, do, and conclude. Here's a key afterwards. But don't look at the key till you actually give it a shot. Try to use the notes that you already have to give you the best shot in this question. Good luck.